Okay, our last section in chapter 9 is called, well, it's 9-10, and it's called Shifting Impedances from Secondary to Primary and Vice Versa. It's a pretty involved title, isn't it? What we'll do is we'll work through this example that he gives us and make use of this thing that we picked up on in the earlier section about the value that of the impedance based on the turns ratio squared. And we'll look at some examples of that and go through this transformation that is shown. And maybe we can actually see something useful for it from it at the end of it. So let's get the figure up here and we'll work through it together. Okay, so at first glance, figure 913 looks pretty involved, doesn't it? This actually is a progression that we're going to go through from beginning at A and working our way through here. And we're actually going to take this and transform it into this at the end of this. So the best thing to do is just to, let's just take this off at one bite at a time and see what we can come up with this. And it's very well laid out, and we've got some really good figures to work through. In terms of, us actually working a problem this involved, we probably won't, but I think it's important that you're able to look at it and understand what's going on. And there are parts of this that we will absolutely use in some problems that we work at the end of this. So initially what we have is the actual circuit, and here's the source, and here is a load on the primary side, which we haven't seen before, and then out here is the secondary side with some additional impedances connected to that. All right, now it probably helps me a little bit to blow that up a little bit so I can see it better and see some of the values here across. Here's some things we recognize, right? Of course, this E2, and also there's some new things here, and they're just defined in terms of what the impedances are. So E4 is in relation to Z4. What's the voltage across that? And E3 is across Z3, and so forth and so on. We've got different currents, right? And so, a lot going on here. This current that we were looking at earlier now has become comprised of a lot of different currents. And, we let's just recognize it at first, and then we'll walk through the progression that he gives us in the text. And then one other little preliminary thing here, is the process that we're going to is, we're shifting these impedances from the secondary to the primary side until we actually get to this, where the ideal transformer is just hanging out here by itself here on the extreme right side. And we can go through this process to where we can equate this to this, okay? And that's what we're working toward. Okay, so here we go. All right, so the first impedance that we shift is this. Now, again, this is actual, but we have this idea that the apparent impedance to the source is this A squared Z from the secondary side. So there we go again with that wonderful thing occurring. Let's see if I can get this dialed back up here. Oh yeah. So I guess we're going to struggle through this all the way to the end. And let me get back to here. All right, here we go. Come on, internet, hang in there with me. So here is Z3, And if I want to shift that to the primary side, what I do is I move it in the same position and I change it to a squared times z2. Okay? So this going to this is done by moving it in the same position and just changing that z2 to a squared z2. Okay, so that's what that is there. Okay, so that's the first thing that I did. Then the next thing that I'm going to do is I'm going to move z3 over. Again, I move it over and I rename it as a squared z3. Okay, and then I've got one more. I've got z4 out here, and I'm going to move it over to here, and I'm going to rename it as a squared z4. Again, because we're thinking about this in terms of what does the voltage source see? Well, think about this for a second. If in this practice, I have shifted all these impedances over to the primary side, what I end up with is this circuit, which all the impedances or loads are gone. And so I'm left with just this transformer here. And so if I'm modeling or trying to solve a circuit, and we haven't really had any circuit analysis where we look at a transformer as a component, have we? No, we haven't. So if I can do this shifting exercise, and I can, since this is open circuit, right, there's no current flowing. So he says, why don't I just get rid of that? And then I end up with this. And so what this shows us is this shifting impedances that gives us a method to do circuit analysis and circuit design on something that we're very much able to do, right? We've got, you know, these guys are in series and it's in parallel with this, and then that would be in series with this parallel combination of these things. And now we have a problem, we have a circuit that we could actually solve by doing this impedance shifting. Now let me read to you just a little bit. It says, in comparing figures 913A and figures 913E, we may wonder how a circuit which contains a real transformer can be reduced to a circuit which has no transformer at all. Is there any meaningful relationship between the two circuits? The answer is yes. There's a useful relationship between the real circuit of 913A and the equivalent circuit of 913E. The reason is that the voltage across each element in the secondary side becomes A times E when the element is shifted to the primary side. And also, the current in each element on the secondary side becomes 1 over the inverse relationship in terms of current when we shift it to the primary side. Okay, so that is how we get to do circuit analysis based on doing this shifting and remembering these fundamental equations that relate voltage turns ratio and how the turns ratio and the current ratios are inversely equated. Okay, now, so let's take this to a little bit further and put some real values here. So looking at 914, what we can see is, here's a real specific example of an application of this. So suppose the real voltage across Z4 is E4 volts, okay, and we're showing that with that meter that's connected across Z4. And I'm also measuring the current through that impedance, through this amp meter here, okay? Then in the equivalent circuit, this Z4 becomes A squared Z4, and it is, given that, in the equivalent circuit, thus in the equivalent circuit, the voltage across this impedance here would be equal to E4 times A volts. And on the other hand, the current through that impedance would be equal to I4 times 1 over A across there, okay? So in other words, whenever the impedance is transferred to the primary side, the real voltage across the impedance increases by a factor of the turns ratio, and the real current decreases by a factor of the turns ratio. So sort of, doing a summary and speaking in general terms, whenever an impedance is transferred from one side of the transformer to the other, the real voltage across it changes in proportion to the turns ratio. If the impedance is transferred to the side where the voltage is higher, the voltage across the transferred impedance will also be higher. Conversely, if the impedance is transferred to the side where the transformer voltage is lower, the voltage across the transferred impedance will be lower than the real voltage. Okay, and again, that is all based on the turns ratio. And then he says in some cases it's useful to shift impedances the opposite way, where we might shift the impedances from the primary side to the secondary side. And that is shown here in figure 916. And all the impedances are transferred from this primary side to the secondary side would be divided by the A squared. We can even shift the source to the secondary side when it becomes a source having a voltage that is given as E sub G divided by A. The ideal transformer now is isolated here, and in this position the primary is open circuit. Consequently, both the primary and secondary currents are zero, and as before, we can remove the transformer and end up with a circuit that we could do analysis on. Okay, so bottom line there is what we're doing is, we're taking advantage of this characteristic of the transformer so that we can actually perform calculations on transformers in circuits. All right, so let me stop there and then we'll do a quick run through in example 9.5 and we'll be done with this chapter.